Hello everyone, welcome to week 11 of this tutorial sessions. We will wait for a few minutes for other people to join. Till then, you can unmute yourself and ask if you have any questions regarding the last week or the previous week. We'll wait for a few minutes. Hello, so let's start. So this week, the topic that was covered in the class was on sequence learning. So sequence learning is when you have a sequence as an input. So earlier you were looking at say words when you used embedding methods such as word to vec or globe to embed your words into certain vectors, and then you use those embeddings for downstream tasks. So then you looked at images, and images are given as matrices, and then you perform some operations on these matrices or these images to capture the local
Hello,
information. Yeah, hello.
are you sharing your screen?
No, no, not yet. I'll be sharing in a few minutes.
Okay.
So yeah. we will be, yeah, so we looked at images where your image is in the form of a matrix. You perform a few rounds of convolution on those images to get some embedding vector, and then you use this vector for downstream training tasks, say classification of an image. But now this week, what we looked at was sequence modeling. So sequences are uh, uh, inputs which comes to you in a sequence. So in images, you are given the whole image as an input, but now you will have say words or some sentences. Say you get one sentence, and the task is to predict what is the next word in the sentence, right? So with the cat is black, so you get the input cat, sorry, you get the input the, then you want to predict the next word, the cat. So once you see that your input is the cat, now you want to now you want to predict what is the next input, which is. So then when you have to model sequences, so you must have seen in the class that we use recurrent neural networks. So I will share my screen. I'll join from my iPad. Let me share. Yeah, till then, if you have any doubts, you can ask it, or if you want to, if you want any other portion covered, so we can discuss that.
So can you revise the sessions for last week?
Yeah, sure, sure.
I mean, like summary kind of that.
Yeah,
Okay.
yeah, so not only last week, the summary of all, so there are two things. One is the loss function, and another is the activation function. So there are different types of activation functions, and there are different types of loss functions. Somewhat like, can we have one session summarizing all the things and connecting all things that we have?
Yeah, so this is the 11th week, and the next after next week we'll have another session, one last session. I think on 22nd, I guess. Yeah, on 22nd. So that will be a general session. In that we will whatever questions you have, whatever general questions over the whole course that you have, we will be covering those there. But if you have any questions now, we can also do it, no problem. But we'll have a session for that where you can ask any question regarding the last 12 weeks of the course. I think you will get a notification in a few days regarding this overall session that you have. So let me share my screen. So first of all, I will Okay, I'll just go through the basics of this week. So this week we covered RNNs, the problems with RNNs regarding your vanishing gradients or exploding gradients, and then we looked into LSTMs and GRUs. So I will cover the architectures of this. There are some other details like uh, why these exploding gradients or problem of vanishing gradients occur. So we will look into all these. And yeah, if you want to cover anything else other than that, you can just let me know and we will try to do that. Okay. So this time we looked into input switchware of the form of sequences, right? So sequences means suppose you have a word. Uh, Suppose you are trying to predict characters, let's say, and suppose you have some word, say apple. So now your input arrives one at a time. Now you get one A as an input, and your task is to have some neural network here, and it predicts the next word, next character P. So now once you have P, you want to have you want to predict P. Now once you see that you have predicted 2P, now given the second P, you want to predict L, and given L, you want to predict E. So this is your task that you have. So the so I will not go into the details of mathematical equations here because that becomes a bit clumsy. So one thing you can see is that the general form of this neural network is same. You give some character as an input, and you get the next character as an output. So you don't need four different neural networks for doing this, right? So so we have this concept of recurrent neural networks. So recurrent means it happens again and again. Because it happens again and again, you can just uh, encode this repeating structure in a neural network architecture. So we'll also look at a code which implements character RNN after we discuss this. So wait a minute. Yeah. So your input can be this network can be shown in this sense, right? That once I have this uh, first layer that takes as input A and outputs P, you can pass on some information to the next stage. So this is at so suppose this is time and you have only one network. This is at time step say one. You have some input A, you want to predict some output P, and now you have learned some information about this that given A you want to do this, and we want it predicts P. So this you have to you can pass this information to the next time step. So now let's say time 2, the second time step, your input is P, it again outputs P. Now you pass this information to the third time step. At third time step, you have now it looks so. So initially it will look at some say blank slate. You don't pass anything. it will just say that okay, this is the start of the word. We don't look at any other function now. But now, once it goes from the first time step to the second time step, it will look at some information, say H1 or S1. Let's just say. So now when I am at the second time step, it will look at A, it will look at S1, and sorry, at the second time step, it will look at P, it will look at S1, and predict the next character, which is now again. Now it will look at S2. So now, because see, here it looks at the first P and knows that it needs to output a second. But here it also looks at a P. If it had no previous information, it would not know if this is the first P or the second. So after this P, it could have also output P and it was wrong, right? So if you need to give some information that this is the second P that it is looking at. So that type of information is shared via this state vector S2. So when it looks at state S1 and input SP, it knows that it has to output P. Now, when it looks at P and the state S2, it knows that okay, this is the second P that you're looking at. So now we don't need to output P, we need to output L. And then it will pass something called some state called S3. It will look at L and it will output P. So now you see this blockwise operation. So this is time step 4. So if you look at this blockwise operation, you see that this this thing is same, right? So it has to take in something as input. It has to take this as input. It has to take this state as input and then output something. So you can just write it. Also, one thing I noted is that because this is a neural network, we have some ways. So the class, I think, uh, these weights were referred as U, these weights were referred as W, and these weights, because these are connection, these weights were referred as, right? So you can just aggregate this whole architecture and just say you have a neural network of this form. Well, you have some input here. Let us say your input is X. Your weights at this point is X. Sorry, U. You need to have some state information. You have some S, and then this will have some W here,
Right.
and then you output multiply with some weights by V, and you output something, say Y in this case. Right. So this is the basic structure or basic unit of a recurrent neural network. So sorry for the noise. So there is some test going on and there's some background noise. अच्छा, आपने-
So this architecture would be remain same for every timestamp.
Yes, this architecture will remain same for every time step because the operations remain same, right? You have one input here, you have some state here, you need to have some W here, and you multiply this thing with the weight that you get at the outer layer, the V that you have. So that is why it is a recurrent unit because it occurs again and again.
And what will be the probable input for, as you mentioned, that S state?
Huh.
Means
So
it's a features or
so it is not a feature. It is as they say, it is a state vector. So by state vector, you mean so suppose you give some A as input, and so your neural network is something like this. So when we pass A, it means you are passing some embedding of a, say you are doing, let's say word to vec. It is not a word, it's a character. So you have something called one hot embedding of a. So it will have, so this is your input, which is a representation of a. You will have some layer here, then you will have some hidden layers here, and then you will have the output layer here, right? So and this will have some weights, say all these are connections, so is all of these will have weights in some sense, right? So you will because you are passing this one hot encoding as an input, you will learn some representations, right? Because when you are looking at auto encoders, what did you see? You have some input x, you go to some lower dimension, you learn some representation, then you go to the decoder and you try to reconstruct x, right? So that means you are learning some representation of x in this space. So even here, because you are passing a, you will also have some input of s from this side, which will have some weight, say w. So using this representation of a and this state information, you will learn some representation. So this representation says that okay, I have looked at a as an input, and before this I have looked at this and this. So that information is passed to the next layer. So that is some latent representation that is being passed to the next layer. Is that clear?
No, sir. Can you repeat again if possible?
Okay. So let me see. So what is the operation that is happening here? So you have some a, right? So let us break this down. So you have some input x, and you are doing a u of x, right? Which is the weight vector here. And now once you do u of x, so what is happening here in this case? So you will get some sigmoid of u of x, something something like. So that means some nonlinearity. Say you have ReLU in that case. So you will get a vector which says that okay, I have looked at the input x, and maybe you will get something like u11 x1 plus u12 x2, and so on, something like this. So that says that okay, I have x as an input, and I have multiplied some weight and applied a non-linearity. Say I have a ReLU of this, for example. So this is an so at this point you will have some representation of a once you go to the linear layer, some vector type representation. Also, because once you get inside this, you will also have this w, right? So w times s, the from the previous layer, s times step. So you have w s of say p minus 1, and these two things are added. So you will have again have some non-linearity here, and you will have some vector of for WST1, and these two things are added to pass it to this output, right? So you, what I'm trying to say is that so forget this neural network. In case of if you are trying to spell some word, you know that if I look at the first P, the next alphabet should be P. But if I'm looking at the second P, the next alphabet should be L. But how will the machine know whether it is looking at the first P or whether it is looking at the second P? So that information, because these are all learnable parameters, right? These U, W are all learnable parameters. So the machine learns that it is which character it is looking at. So that information is passed by the state vector. So at this state, so at time step 2, your system is at a state AP. At time step 2, at time step 3, your system is at the state say APP. So it knows that if it is at this time step, the next prediction is P. If it is at this time step, the next prediction is L. So this is the state of the system, let's say. So this state information is passed by this S1 vector that you have. Uh, do I need to explain anything more?
So the non-linearity used in RNNs is mostly ReLU.
No, it need not be ReLU, because once you go into LSTMs, you see that they use sigmoid in some sense. So some examples also use 10H, but it depends on which type of RNN you are using. So ReLU is
Yeah,
one favorite thing,
so
but you can
suppose not
also
LSTM, suppose the raw ReLU in uh,
ah,
raw
so
ReLU
or
in
raw
RNN.
ReLU, yeah, yeah, you can use raw RNN. Yeah, you can use sigmoid in. Oh, sorry, you can use ReLU in that case if it works. So that is
Okay,
again a hyperparameter. You have to check and see which one that is.
okay.
So yeah, is the concept of the state vector clear?
Yes.
Okay. So hmm, so let's see an example for this. So okay. So yeah. So I will not go through this backpropagation through time because that involves writing a lot of mathematical equations. But the basic idea of that thing is, because you are if I open this up, so it will look something like this, right, which we have here. Okay, this. Here's something like this. So these are the 4 time steps, but you are using a recurrent neural network here. So at this point, you are predicting at this point, you are predicting at this point, you are predicting at this point and this point, right? So now your losses are computed at each point. So you have a loss at time t, time 1, loss at time 2, loss at time 3, and loss at time 4. So once you go through all of these characters, so you have some loss which will be a sum of all these 3 losses, right? Total loss, say L, is L1 plus L2 plus L3 plus L4. And now you have to backpropagate it through all of the previous process. So what I'm trying to say is, if I am expecting some character, say E at this case, in this case, and I get some other data, say suppose for example I get G, which is not correct. So that means there is some error that we have. So that error has to be propagated through the fourth time step, and because the fourth time step depends on the third time step, it has to be propagated through a third time step, which depends on the second time step. So it will also be propagated to the second time step, and so on till the first time step. So that is what backpropagation by through time means. So you look at a loss in this case, and using this loss, you backpropagate and update the gradients or update the parameters which you have across all the different time steps. So you will be updating the parameters once, but the gradients have to be calculated with respect to all of the time steps that you have seen till now. So that is what the concept of backpropagation through time is. Is that concept clear? Because uh, it may not be very easy to think about it.
So here we have to calculate the gradient at every time stamp, or we have to apply the reverse engine means back propagation for the till the first level, and then I have to calculate the gradient.
So generally what we do was, if you remember backpropagation, you compute the derivative of loss with respect to the output of the last layer, say OI. So now OI depends on, say, the previous layer. So you'll have dou L of dou I. So OI will depend on the activation of the previous layer, say uh, some A, L, and we do a chain rule, right? Because we have to go through
Yes.
all the layers. So now in this case, you are getting an error in at this point. So uh, you're getting an error at this point, and now you will compute your derivative with respect to the parameters at this point. But now once you compute the derivative with respect to the points at sorry, with respect to the parameters at this point, so you will also have some s here, right? So that means you have to
Yes.
compute your derivative with respect to s also. But once you look at s, we know that s also depends on s2. So once you compute the derivative with s3 with respect to s3, that means you will also have to compute it with respect to s2. So which will update the parameters because the parameters will be same, but it has a dependence on the previous layer. So once you compute the derivative here, it has to be with respect to s3, s2, and s1. So that means you have to go through all of the stages, all of the state spaces that you have seen till now, and you have to compute the derivative with respect to each of these time steps. So that is what backpropagation by time through time means, that you are at a time t, but you have to look at derivatives with respect to all of the previous time steps. Is that clear?
No, that is, I got your point, sir. But
Hmm.
what I mean to say, suppose consider that for the input L,
Yes, for this one.
uh,
Huh.
yes, fourth one, that timestamp 4. So over that, I have calculated the gradient descent
Okay.
now. And so that gradient descent is calculated based on S3, S2, and S1.
Yes.
Am I
So this is
understood correct,
just
right?
huh. Yes. So this is just the input. You will have a v here. So your parameters will be v in this case. You have some w here, and you will have some uh, I think u here, right? So your loss with respect to this, your loss with respect to this, and your loss with respect to W. So when we go to W, we know that it depends on this state space that we saw before. So now that means you'd also need to compute with respect to S3. So once you go through S3, we know that it depends on S2. So now you will also need to compute through S2 and so on. So because you have to compute with respect to each of these parameters that you have, so it leads to having to compute through to the first layer. That is what I'm trying to say.
Okay. And is there any role of like we have the three types of gradients, like as you have mentioned that stochastics, batch,
Oh,
and
okay.
mini batch. So how those gradients are playing their role in this case?
So those three SGD or mini batch, those are only algorithmic. So if you are
Okay.
looking at the full data, so those two are actually two different. The backpropagation that I'm saying. So let me write it down. So for gradient descent, your update rule is W minus beta times gradient of the loss, right? So this is your update rule, and whether you do stochastic gradient descent or normal gradient descent, this update rule remains same. Only thing that depends is that is different is how do you compute this, right? So because this gives us your gradients that you want to compute. If you compute it for the full data set at once, you have your normal gradient descent. If you compute it only one point at a time,
Okay.
so that means you have a stochastic gradient descent. So even in this case, you will need to compute this for each of these. So one batch is your each character. This is your one data point, this is one data point, and this is one data point. Same. So then you'll have to compute it with respect to each of these data points. So that is done through backpropagation. Your whether you use stochastic gradient descent or gradient descent does not matter. but your back propagation, how you are doing back propagation, that matters whenever you are using, say, a recurrent neural network, because you have to do it through time. I hope that is clear.
Yes, yes, now.
Okay. So yes, so because you are doing this back propagation through time, there are, you can rewrite some mathematical equations, and it basically shows that if your gradients are, say, if your gradients to W are very large, say here you have, say, some 100, and here gradients at this point is, say, 1,000, here it is, say, 10,000. So by the time it comes to S1, it will be a very large number, right? Say 10 to the, I don't know, 6, 7, 10 to the 7, which is very large gradient. Yeah. That means that point will have a very large update, but other points may not have some large update. So that is an explosive gradient that you have. Because you are back propagating through time and you're not controlling your gradients, you have a large gradient in that case. And the reverse can also be also happen. That you have very small gradient. So suppose you have a gradient of 0.01. Here you have a gradient of 0.001. Then again you have a gradient of 0.001. So by the time you back propagate through this, so this will be very small, like 10 to the minus 6 or 7. So if you have very small gradients and you look here, if this is small, that means you won't update your weight much. So training will not be good. That is, your loss will not decrease much. So these are two problems that happens due to back propagation through time. And there are some tricks to, not tricks, there are some ways to minimize that. Say you use some weight normalization or such techniques. So that has been covered in the lectures and requires some question. I will not go through this. But but the reason why this happens, why exploding gradients or vanishing gradient happens, I hope that is clear. Okay. So next, so next we'll look at LSTM, because uh, because we saw that uh, because we know that if you are say reading something, you know that not all parts that you're reading are important, right? Say I have a sentence, let's say, I want to say, like, I'll take an example from the course. The movie was long, but good. So there is a task in NLP, natural language processing, which is called sentiment analysis. So that basically wants to say whether a sentence that you're giving, whether it has a positive sentiment or a negative sentiment, that whether you are saying something positive or not. So this is a positive sentiment, right? This is a positive sentiment. It basically says that your movie was good. So when you are passing it through some recurrent neural network, so here I showed you a recurrent neural network which takes only characters as input. You can also have a recurrent neural network that takes your words as input. Say, suppose your uh, task is predicting the next word in the sentence. So you will pass the, so it will learn that it has to output movie. It will pass movie. It will learn that it has to output was, and it will also share some state space and so on. Once you pass but, it will learn that you have some thing called, and you have some state st minus 1. So that is this was a character level RNN, and this is a word level RNN. I'm saying. So suppose you have a similar task, but your task now is to predict whether your the sentence that you are looking at, whether it is a positive sentence or a negative sentence. So how do we know that it is a positive sentence? We know this because we have this word good. So we want that our network should know that this good is there in the input that you have given, but this long was there, but we don't want the same uh, network to know that okay, this long word is there. That is because that shows that it is a negative sentence, but actually we know that it is a positive sentence. So that means we want the network to selectively look at it. We want the network to say that okay, I will only look at this part of the input. I don't want it to look at the other part of the input. So this selection, uh, how to determine which words are important for this sentence, which words are not important. Say these words like the, was are not important because they do not change anything about it. So that requires something called as LSTMs. So you don't need to look at everything. You just look at whatever is relevant for getting the output. So LSTMs are uh, defined in such a way. So I will straight away go to the architecture. Uh, Let me draw the architecture.
Like before this, like can you explain the issue of exploding and vanishing gradient?
Okay. So suppose we have some simple array. Let's say in this case, right? And now you want to, so you want the true class that you want to predict it is, here is E, and you got something like C. So that means you are not predicting correctly and you get an error. So you have to propagate this loss, right? Using this loss, you have to update whatever is learned here. You have to update these ways, and you have to update all of these ways, whatever was learned in the previous time steps. So that means you do a back propagation from here, and then you use this back propagation or use the back propagation to update this weights W. So because these weights V and U are shared, so this will be updated easily because it just depends on the current input that you have. But if I look at W, this W depends on the state which was coming before it, right? So say for this step, this W depends on the state S3. Now again, if you go here, here you see that this W here depends on the state S2. Here it depends on state S1 and so on. So if you want to compute the gradients at this step, at time step 4, you still have to look at the gradients that occurred beforehand or before in the previous time steps. So that means gradient at this step, time step 4, depends on the gradients that occurred at time steps 1. And if you write out these gradients you write out these equations, it is basically a product of all of these. Say gradient of these times gradient of this and gradients of this. So because you are doing a product, now let's say that here your gradient was say 100, here it is say 1000, and here it is say 10,000. So when you're trying to create or compute the gradient at this time step, this will be like 100,000 times or 10,000 times 1,000 times 100, which is 10 to the power 7. So that is a very big number. So that will be a very, uh, very big gradient in your calculation, and you don't want that because it is not, it does not make sense, right? So one point will have a very large gradient, other point will not have some any gradient at all. Or you can have the other case. So here suppose a gradient is small, say 10 to the minus 2, and here also say you have gradients which are small like 10 to the minus 3, 10 to the minus 3. So because these are multiplied when you are computing the gradient at this step, you will have some gradient like 10 to the 2, 3, 3, 8, 10 to the minus 8, which is very small. And we know that if your gradient is very small, then you won't update anything because this quantity becomes small, right? If this becomes small, then WT plus 1 is equal to WT. Your network will not learn anything at all. Your losses will not decrease at all. So that is why.
So this issue is with every back propagation, or it's just with RNN?
So actually it occurs with a lot of. So if you remember when you are discussing this logistic function, right? For the sigmoid function, say. So in this sigmoid function, what we saw was if your reactivation is large, your gradient becomes 0 in this case, or your gradient becomes 0 in this case. So if you have some in the back propagation, if you have something which has a very large activation, you get 0 gradient and you basically don't update anything. So that was also an example of vanishing gradient. So that is why instead of sigmoid, we saw that okay, we can use a ReLU function. So because for ReLU function, your gradient is bounded. You have a gradient of 1 in this case for ReLU function. So it happens. So it happened for sigmoid for a different region, but here it is for a slightly different region, but it happens in a lot of cases. Yeah. So for here, because of
So
this,
sigmoid, in sigmoid, the issue was only vanishing gradient. It was not exploding, I believe. But
yeah,
here, it's
uh, so because if you have this, so if you write it down, you have a product term like gradient at time step 3 times gradient at time step 2 times gradient at time step 1.
yeah.
So
So in
because of
sigmoid, the only issue was
Mhm.
vanishing. Na, it was
Yeah, right.
never exploding.
No,
Okay.
no, no. Mhm. So if you have some other activation, let's say your activation is uh, something like this.
Then
Uh,
with the ReLU, it can explode.
for ReLU, it cannot explode because so this is your ReLU activation. Suppose if your x is less than 0, your gradient is 0. If your x is greater than 0, then you have the input as the activation. So the slope is always 1. Your gradient is always 1 in this case. So it can neither explode nor it can uh, have a vanishing component.
Okay, so because the slope is always one.
Slope is always 1, right? So now coming to LSTMs. So for LSTMs, there were three things. Or before we go to LSTM, there are three things, right? We want to have selective reading, or before selective reading, we want to have selective writing. We want to have selective reading. We want to have selective forgetting. So you want to have all this because we saw, right? We don't want to look at these inputs like da, was. These things are not important because they don't contribute anything to the one to the task that is one, or even part part may be useful. I don't know. So that means you don't want to read this, right? So this is selective reading. You only want to look at the important part. So movie was important, loop was important, long was important, good was important. You only want to look at this part. So that is selective reading. Or you can also say if you want to forget some states, so then you have something called a selective forgetting. Or if you want to write this output to some other state, so you don't want to write the output of say the score that you get from this from a given time step. You don't want to write it for the future time step, so then you have some selective writing in that case. So if you remember uh, the structure so of RNN, you have this st minus 1, st minus 1, you have this xt. So these are the two inputs you have, and you output some st. Right? So first, let us look at this st minus 1. So you get st minus 1 from the previous time step, right? So once you get st minus 1, you say that, okay, I am getting this much information from my previous time step, but let me say that I don't want to look at all of this. I just want to look at a few indexes from this. Say from st minus 1, you are getting some inputs, say uh, 0 0.3, 0 0.2, 0 0.8, 0 0.01 or something like that. And now I want to say that, okay, I'll only want to look at only want to look at this coordinate, and I only want to look at this coordinate, and I don't want to look at these things. So that is, you are selectively writing onto S1. So this is ST minus 1, and you are writing onto ST minus 1, and you want to remove some things. So that means you are selectively writing it onto ST minus 1. So there you use some vectors or some gate called the OT minus 1. So the output of T minus 1. And this is a learnable parameter. You don't have to say specifically which things I want to forget. The network will learn, okay, these things are important. So network will learn, okay, this is important, this is important. So it will have, once you do this operation, it will try to learn that these two steps must be remembered and these two steps can be forgotten. So it will learn some OT minus 1 vector in that sense that, okay, we don't need this. So once you have the selective writing, the next part comes here, because st minus 1 is, so the output is generally given by, I think, ht minus 1. Uh, so now what you have is that your uh, your input contains w. You have ht minus 1 here, and then you have some t in this case, which can be some vector, and you will have some non-linearity here because you are doing an operation. And now once you see some state and you see some input, now again the network will decide that, okay, all of these given this state, all of these are not important. So for the example of apple, hmm, say at time step 3, let's say, it is now the state says that, okay, I have looked at a, p and p. So your input is p in this case, so this is your input, say. Now the network decided, okay, my input is p, and previously I have seen p and a. But previously, whether the network has seen a or not, it does not matter, right? Because it knows that if you see p previously, it should output l in the next step. So it will try to selectively write only the state of ap, or the selective write step will only say that, okay, I have seen a p at this step. It does not matter whether I have seen a or not, because that is noted. If if you are seeing p, it must have seen a beforehand. So that is selective writing actually. So selective reading also, you will have, like, for this example, let us say I don't want to look at this da and was. So given this state, if this is, say, was, and some embedding, and so it will not be word actually. We'll have a sentence, maybe sentence level RNN. I'm not sure, but basically you don't want to look at all of these inputs here. So you forget this. So that means once you get this input, you get some thing called ST, and then you again you have some learnable gates, say IT. So IT is basically, it says that which points I want to keep, which ones I want to remove. So you do some operation of IT in this case, and then you have and you go into the, because now you are ST. Now you want to produce HT, right? So your HT will again look at whatever you computed till now, and it will say I want to keep some things, I don't want to keep some things. So given this mm, given these operations you have done till now, I'll just forget some of these things. So that forgetting is done. Uh, hmm. So you add this st minus 1 vector that you had here. So this is not clear to me, so I think you should go back and look at the lectures. Uh, you do one more operation here, and then uh, you do one more operation here, and then you say that okay, I only keep the relevant parts of the data that I have seen till now. So this is your selective writing part. This is your selective reading part here, because this sigma is a activation that you have. It gives okay positive or negative, and then you forget whatever you don't want and you keep whatever you want, and then pass that this should be HT. Pass that hidden state to the next layer. So I hope this whole flow is clear. Any questions? Okay. So yeah, so this RNNs and LSTMs were the main. So yeah, there is another thing called GRUs. So GRUs are basically a slight modification of this LSTMs, where you instead of say some output gate, you have some output gate here. I think here you have an output gate OT. Instead of that, you just replace OT by say I1 minus IT. So IT is what you want to keep here, and or what you want to forget here, and this is what you want to keep here. So GRUs are just a type of LSTMs, you can say, and these are called gates. These IT, OT are called gates because they check what information is coming in and what information is going out. That's why they are gates. Okay, so if there are no more questions, I have some slides or some notebooks I have prepared. We can go through this.
So we have to learn the equations of the gates and the states.
No, that is not important actually. Those equations won't come. So it is a good thing if you can given a block diagram. Say someone gives you what the diagrams, this architecture. If you can derive those while looking at the diagram, then it is good. You don't have to learn it actually. So suppose I give you that my hidden my hidden state is st minus 1. I have some input gate or I have some for gate ot minus 1. What is the output of this? So if you know how to derive this, so this is basically some function, right? W times ht minus 1, or ht minus 1 is, say, you get some ht minus 1. You do some pointwise operation, you get ht minus 1. And once you get ht minus 1, you apply weight on the ht minus 1. And then you sum up with this xt minus 1, which have some weight u. Then you have x or xt minus 1. And you take a sigmoid of this. So we just note how to do this by looking at this diagram. You're looking at this flow, right? st minus 1 comes through. So st minus 1 comes through here. It is multiplied with ot minus 1. Then xt minus xt comes multiplied with u, and both of these are added up, passes to sigma. So by looking at this diagram, you can just see how the equations will shape up. So if you know how to do this, that should be fine. No, you don't have to learn that this happens and this happens. Given some diagram, you should be able to derive this.
Okay.
So let me share a note. So is my screen visible?
Yes.
Okay. So this is a so this you can find such notebooks in tutorials of PyTorch. So PyTorch has this tab called tutorials, even in PyTorch or even in TensorFlow. So do you give some working notebooks, and you can just run those. So the ones I'm taking here is a character level RNA. So the problem that I have here is that given some name, say in this case, uh, say I say that this is some last name you have Abraham, and you want to say what category does it belong to. So according to the data set, this Abraham belongs to uh, the class French, or you can also have maybe Indian, and then you can just do that. So the data set is also available in that. Let me share the link. Wait. Okay, so it is a text generation tool. So okay, so the task that we have is a text generation task. Suppose someone says, say, what are some Spanish surnames? So these are some Spanish surnames. These are some Chinese surnames, and so on. So we use recurrent neural network for this task. So if you are running on Colab, so you can just download it and run on Colab. If you have this, so if you are using some data set, so you have to download data set to your Google Drive, and then it will you have to do this things so that it connects to your so that it is able to connect to your data Google Drive. Huh. So now it is trying to connect to your Google Drive, and it will once it connects to your Google Drive, you can just use your you can use it as your drive. Yeah, now I can access the data set that is stored here, and then so I have stored my data set at something like this. and it will try to find it in my drive. And so these are some Python functions which are helpful for writing and reading to files, and even OS, as you might be aware, uh, is helpful for finding links to data files in your system. So there is a helper code here for uh, because the input that we getting is not only English, it will have some things. Say for this example, this name say Sluraski. So it has these characters like S, which has some dash on top of it, A, which has some dash on top of it. So these are not Unicode; these are in Unicode characters, and you want to convert it to ASCII so that your embedding becomes easier. So this is a helper code for this. Now we'll look at how the data set looks like. So for example, we had this Sluraski in some other embedding which had this S and A in this way. So now you see that these are all in ASCII embedding, does not have the special characters. So now let us see what are the names. So suppose I want to say what are the surnames available in French. So I can just say that it is stored is not in French. Okay, there must be some error. Okay, so while reading this file, there must be some issue. Okay, I must have deleted the file. Let me see. There should have been it. Oh, it is not able to read anything. The path is wrong. So yeah, these are the categories. So you have French, you have I think this is Japanese and so on. So now if I want to see some example for English, and have this about FD, these are all English surnames that are data set. So now when we look at word to vec, what we are trying to do, we are trying to say that okay, this word cannot be understood by the machine, so we want to do some encoding for it. We want to convert it to a vector and then pass it through the input, or pass it as an input layer. So here, what you're trying to do is you want to encode each letter. So here you have A, B, B, A, S, or you have A, B, E, L. You want to encode each letter because this is a character level RNN. Your output or input will depend only on each specific character that you have. So you are saying that let us make a one-hot encoder or one-hot encoding for each of these letters. So which is of size say 1 by number of letters. So say B occurs in the second position, right? So we'll have zeros in all of the places, but we'll have only one in the second place. And now I'll check what are the number of letters present here. So it is 57 in the whole data set. So n letters we get here. So it looks at all of the data that we have seen till now and then updates it. So once we have this, because the architects or the network will expect that you are passing a matrix or a vector as an input. So once we have this encoding, we will need to convert it to a vector. So PyTorch has this uh, way to convert. So say let me run this. So here, what it will do is it will find all the letters that you want to give and find the numbers for that, and then given this input say line, it will first make a vector of all zeros, and then the ones where you want that the index for the specific letter, it will be marked as one, and then we are converting it to a tensor. So tensor is basically like a matrix but of higher dimension. So vector is of one dimension, matrix is of two dimension, and if you go then more than let's say 3, 4, 5, so those are called tensors. And PyTorch or TensorFlow, because it is there in the name itself, they always expect that your input is in the form of a tensor. So if we look at it, we have this letter Jones, right? So Jones has Jones, 5 letters. So that means it will have a embedding for each letter. So we saw that number of letters was 57. So each letter will have a 57 dimensional input, right? So for J occurs at position 10. You have a vector of length 57, and in it will be zeros at all places except the position 10. There will be one in that case because that is the embedding for J. For O, it will be at a different position, maybe 13 or 14, I guess. So because there are 5 letters, so for each of the letters, so there is 57 length vector. So that is why we have a 5 ones for 57. That means we have 5 letters or 5 letters. Yeah. This one just says your vector length or dimension is 1, and each one is of length 57. So that is this is what it refers to. So is this clear how you are getting this 5157? Are there any doubts? Okay. So now let us see how to create a uh, RNN for this. So we saw RNN contains of this input that you get the X. We have a previous state information, and then we have the output, right? So because we have to this is each of this RNN is a here neural network, you also have to give the size of the hidden layer that you have. So this population I2H, okay, I have not written it here. Let me share this instead. Hold on. So actually, I designed a notebook for this, but now I'm keeping this as a to-do. Okay, let me share it. Okay, let me share this. So I'm sharing the link of these tutorials. You can also look at some other tutorials that you want. Meantime, that should be connected. Okay, this is connected. So here you will see that I'm trying to show the embedding for the letter J here. So you see there is a one for the embedding which for the place where it says it is a J. Because okay, so this is a capital J, right? So for small characters you will have some 26 numbers or 26 spaces, and for capital characters you'll have 26, 52, and you will have some extra spaces like or extra characters like this one here. Uh, Full stop, comma, and semicolon, and this single quote. So you have a total of 57 in that case. So this is what the embedding of J will look like. If I change it to say small o, it will be different. So now you see the one appears here. So this is how the embeddings for each character look like. And then you have 5 cross 1 cross 57. So which is you'll have 5 times 5 copies of this. So if I just remove size here, so you see this is how the embedding of zones will look like. So this is your J embedding for J, this is for O, this is N, this is E, and this is S. So you pass this whole tensor, you pass this whole tensor as an input to your neural network. So uh, now you design the neural network that you have. So that
So tensor is three-dimensional.
not necessarily three-dimensional. Matrix is two-dimensional, and anything greater than that, you have a tensor. So that means it can be three, it can be four, it can be five, and so on. So suppose you have an image.
So this that is printed, it's more than two. It seems to be two.
This is three-dimensional. So 5 is the number of. So one dimension is this 5. So 1, 2, 3, 4, 5. So that means you have 5 characters, and one says that each of these is a one-dimensional array, and the 57 says that each of these one-dimensional array is 57, has a length of 57. So if you have an image, for example, so suppose you have a 100 cross 100 image, so that is a matrix 100 cross 100. But now if you are doing say mini batch SGT, so suppose you take 10 images at a time. So if you stack these 100 images back to back, right? So now you have 10 cross 100 cross 100. So that becomes a tensor. Or suppose for example you have a RGB image which is of 100 cross 100. So RGB image has 3 channels. So then you have 100 cross 100 cross 3 as the size of each image. And now if you're stacking 10 of these RGB images together, you have 10 times 100 times 100 times 3. So then it becomes a 4-dimensional tensor.
Okay.
Uh, you get it, right?
Yeah.
Okay. So so now you want to design the RNN here. So I will show the diagram of RNN in a separate one. Let me see. Wait. Okay, it seems the diagram is not clear. Okay, let me show you. So this is the RNN that we want to show. So you have, so forget this category for now. You have this input and there is some combined layer, and then you want to pass it through input through the output type. So combined is basically, sir, you saw, right? You have this XT and you have ST minus 1. So this ST minus 1 comes from your previous layer. So here, as you can see, this hidden comes from this hidden of the previous layer. And when we do combine, because if you remember, you are doing some U times XT, which is weight matrix times the input, and then you are doing some W times the ST minus 1, the previous layer. So this combined function or this combined block here does this combination, and then once you have this, so now you, if you remember the diagram of RNNs correctly, so now you compute the hidden unit and pass it to the next layer, and you also pass it to the output, right? So because there are two outgoing arrows, so this I2O goes to the output, and this I2H goes to the hidden thing. And then once you have this output and this hidden, you combine it and do your downstream task. Say you do some dropout, you because it is a classification task, you need some softmax, and then you output it, and you give all of these. So like we saw it Apple, right? A given an input A, you predict B, and then you use B as the input for the next step. So similarly, given output, you use it as an input for the next step, and the hidden here, you use it as an hidden information for the next step. So is this diagram clear what we discussed for the architecture of RNN, and this diagram, is this clear? Okay. So this is what we will try to implement in this in PyTorch now. Okay, so there is like you saw, there is this input to hidden architecture which takes your input size and plus hidden size. So this means if your input is a vector of say 20 dimension, and the hidden output that you are giving is a 10 dimension, so now it will just place the hidden vector below the input vector. So earlier your input was 20 dimension and your hidden is 10 dimension. So on top you will have the input vector, and below that is the hidden vector. So now we'll have a 30 dimension vector, and then the output. So because you want the hidden to be of 10 dimension, so your input plus hidden will be you will have a 30 dimensional input here, and you have a 10 dimensional output here. So this is a linear layer. So linear layer, the parameters that we will give is what is the input dimension that you want and what is the output dimension that you want. So here you are giving 10 plus 20, 30 as 30 dimension as input, and you want the output of 20, or sorry, 10 dimension. So is this notation clear? Because this is how you define a neural network in PyTorch. And again, if you remember the H2O part that we saw just now, you take the hidden size that you have and you want the output size. Uh, so output in this case will be the task that we are trying to do is a classification task. So given some surname, you want to see what type, what is it, whether it is French surname or it is English surname or so on. So that is your output size that you have. And first to define what are the different types of layers that you have. So you'll have some I2H layer, you have H2O layer, and you have a softmax layer. So this part below init is just the definition of different types of layers that you want in the network. And then now you want to say that, okay, how does my information flow through the network? How does my data flow through the network? So that part is written in this forward function. So forward function, whenever you are using PyTorch, you will write this forward function, or if you are using TensorFlow, you will see that there is this call function. That call function is exact same as the forward function that in PyTorch. So this torch.get is a concatenation function. Concatenation is basically you have this input vector and you place the hidden vector below it. So earlier your input vector was of 20 dimension, you place this 10 dimension hidden vector below it. So this combined is now a vector of size 30. So you pass this combined to I2H and you get some hidden representation. You pass this hidden representation to the output via the hidden 2O via this network. So when I say combine goes to I2H, it means this combine is a 30 dimension network, and now I am 30 dimensional vector, and now I am passing it through this I2H linear layer. It should give us an output of size 10. So that means it passes through the linear layer and gives an output of size 10, which is stored in this hidden variable. Similarly, this hidden variable, as you can see, it passes through a linear layer and gives an output of output size. So now you do an output softmax of this and output whatever hidden you have and hidden here. So that is how you, so the number of neurons in the hidden layer I set is 128. And this is how you define a neural network, a simple neural network. Is this any doubts in this? So if you have some, say, if you're working on images, you will have some convolution layer, right? So you will define some conv layers here, and you in this forward function you will show how to pass through these convolution layers. So your data will go from conv1, it will go to conv2, and so on. So you cannot change the names of this function. It it is always named forward or innate or hidden. So okay. So now I created my network, and let me see what is the output of this. So I'm not training the neural network at all. I'm just seeing what output it gives. So I'm saying I have an alphabet. I have a letter A. I say that my hidden is a vector of all zeros. So this towards the zeros mean you have a vector whose every entry is a zero, and it is of size n hidden. And I pass this input and this hidden dimension, and I get some output. Let us see how output looks. Oh, we have done this below. So not this. Okay. So again, I am passing this word Albert as an input. It is converted to the. So now, okay, let me check. So how many alphabet letters are there? 1, 2, 3, 4, 5, 6. So what will be the dimension of this input vector? Anyone? So this will input will be a tensor. So what will be the size of this? Can anyone say? I will not print it. So there are 6 letters, and each letter will have an embedding of 57. So what will be the size of this input tensor? Anyone? No one? So we have 6 letters, like, so the first dimension will have a size of 6, and because each letter is of 1 by 57, so you have 6 cross 1 cross 57. Okay. Tensor object. This is this. Yeah. So we have six letters here, and each is of size 1 by 57. So this input tensor is of size 6 cross 1 cross 57. And if you see the output that we had was a softmax of these, right? Softmax of these. So here we are outputting this. So how many classes are there? It is the number of surnames that you have, French, English, and so on. So if you count, it is like 1, 2, 3, 4, 5, 6, 7, 8, 16, 17, 18. So this is an 18 class problem, and this output gives us the probability or log probability of uh, belonging to that class. So for example, it says that it is something called minus 2.9336. It means that if we process it, if we take exponent of this part, it will give us a probability of Albert belonging to, say, this is, say, for example, this position is for German. So what is the probability of Albert belonging to the class German? So this output is a vector of all probabilities of belonging to different class. And if you see here, so because we are using softmax at this stage, at the last layer, whenever you are doing a back propagation, it will go first to the softmax layer, then from softmax it will go to the output layer. From here it will go to the, okay, it will go to the hidden layer, and then it will go to up to the combined layer, right? So if there is something called a grad function, which is equal to log softmax backward, it says that it gives an information that okay, your output is now the vector that you see now is the output of a log softmax function. That is, you have the softmax function, you take a log of it, and the gradient that we want is given by this function log softmax backward. So that has already been defined in PyTorch. So whenever you are training the network, it knows which gradient function to use to compute this gradient during back propagation. I hope that is, any doubts on that? Okay, so let us train the layer, train this network. So again, because it is a multi-class problem, and your system will only understand uh, numbers. So again, we have to get back what those numbers mean, right? So this is a small function for that. So if say output is, say, something called 10, or in this case, here output was this quantity, right? This is your output. So this output means that it is predicting that their surname is of type Italian. It is an Italian surname. So now we create some training examples. Say training examples means we want to train this network, right? So now from the German class, I am taking this as the input, a Berhard. From Arabic class, I am taking this Safar as the input, and so on. So this is my training data now. And now let us look at, before training the networks, we need to look at what is the loss function that we want. Since we are using a logarithm of the softmax function, so in this case, this is a loss. So if you do not know this, don't worry. With practice, you will know with which activation you will use which loss function. So in class, you must have seen that whenever you are doing a cross entropy or doing softmax at the last layer, for classification, you need a cross entropy type of loss. So this NLL loss is a, you can say it is a type of cross entropy loss. You don't need to know the details for this. It comes with practice. So I'm saying that the loss function that I have for now is this NLL loss, negative log likelihood loss. And so we'll be using gradient descent. So the learning rate, I am saying that Okay, let my learning rate be say 0.005. So this is the training function that we have. So what does a training function do? It will initialize the hidden weights. This zero grade says that okay, initially I want all my gradients to be zero because I'm not doing any training at all. And now this loop, it goes over all the inputs that you have. So if you remember for RNNs, you take the hidden layer of the current time step and you pass it as an input for the next time step, right? So that is what you're doing. So this is the RNN. You take the hidden layer of the first time, previous time step. So initially it will be zeros. Otherwise, you will have some non-zero vector here, and your current input. You run RNN on it. You get some output as well as the hidden state. Now this hidden state will be the hidden state input for the next, sorry, for the next input that you have, and then this will continue till it looks to all of the data points that you have. Once you have that, it will calculate the loss. So the loss is you will output something here, and the actual outputs should be something defined here. So category tensor was defined in this case, what will be the uh, categories for each of the training examples, and based on this it will create the loss, right? And now after creating the loss, we know the next step is back propagation, so recompute the output. So that back propagation is done by this backward call that you have. And now what we have is we want to update the weights, right? So that thing is done by you go to each of these parameters and you add this a gradient that we get from there. And then this is the whole training process that we have. And say let me say that I want to run it for, so this is very big, I want
So
to run
this
it for one.
backward will be doing back propagation through time.
Yes, in this case, it will do the back propagation through time. So given the structure of the network, it will know how to, it will create a copy of each of these gradients that it needs to compute, and it will compute those gradient automatically. So that process has already been written. You don't have to rewrite it if you are using say PyTorch or TensorFlow or any of these libraries.
And then here in alpha, why is it minus learning rate?
Uh,
Oh,
so
the
yeah,
next
this
code
one.
in the yeah.
So uh, this is basically you have WT minus one equal to WT minus eta times. So alpha is eta in this case, or eta times your gradient, right? So this is your gradient, and this minus learning. So this is your gradient. This is grade of L and minus learning. You are multiplying these two and adding these together, right? WT minus grade of alpha t. That is why you have a minus sign here.
Okay,
So the update step of the gradient descent.
okay.
Okay. So now say I want to do this for 1000 iterations, and I will print, oh, let me do 10,000. I will print the these losses every 5000 iteration, and I'll plot it every 1000 iteration. So current, I track which are the what are the losses I get till now, and I call the training algorithm here. And after every 5000 iteration, I'll check what is the test loss that I am getting. So let me run this. It will take a few minutes. So now it is training the network. It is creating the calculating the loss, doing backward propagation, updating the weights, and then again training the loss. So here you see it is showing some output. So now my loss is at 5000 iterations, my loss was 2.077. After 10 iterations, our 10,000 iterations, my loss becomes 0.89. So clearly there is a decrease in losses, right? Let me increase this. Say I'm doing 30,000 times. So after 5,000 iterations, I get a loss of, so don't look at this, I get a loss of 1.5. After 10,000 iteration, I'm getting a loss of 0.8. So that my loss is decreasing. And that is what we want, right? We want my loss to decrease. But now see the loss increased. So this is because we're using a stochastic gradient descent. So see, my loss is increasing each of these step. Okay. So it learned some good parameter at around 1000 iterations. So it is giving us a minimum loss in this case. But if we train it further, the loss increases because now, because it is a stochastic gradient descent, it is not at a good, uh, it has not find the good parameters. It found the good parameters here, but since we're again updating it, it went away from the good point and it is at a very, it is learning some very bad weights. So when our loss is good, we have some correct, like, so this Saraf was an Arabic word or Arabic surname. So it is a correct prediction. And all these three are correct. But once our loss increased, that means we're not learning good weights. It we started giving wrong results. So like in Kudal, it is an English, but it shows that it is an Irish surname and so on. So this is what happens in a training procedure. Now let us look further. Hmm. So this is how the training losses happen. So as you see, the training losses decrease. Uh, all losses. Oh, acha. So it is dividing by this plot again. So there is some issue here. So it should plot all of the losses you get across all of this. And now we want to check how it behaves on our test data, right? So let me again, we know that at 10,000 iteration, it gives us good results. That means, so this is a, so what I'm doing is a type of hyperparameter tuning. I saw that at 10,000 iteration, it gives us good results. But if we increase it, it does not give us good results. So now I know that 10,000 is a good parameter to set. So that is a type of hyperparameter tuning that I'm doing. So I will just say that, okay, I'll just train it for 10,000 iterations and then use it for testing because that gives us the minimum result. So each time you will get a different loss because you are random, because you are randomly creating this data set. So because you are just randomly selecting some indices and saying that I want this part as a data set, I want this part as a data set. So you will get, because the data is changing, you will get different losses each time. So now say for this example, we get a loss of around now 1.9. Let us see how it behaves. Yeah, so the loss function first increases, then it decreases. So because this is stochastic, right? Uh, if it was gradient descent, it would have gone straight down. So let us check how it works on a test data set. So I have written this. I am not. They have written this testing part. I will just run it here. Okay. So I am saying that So I'm saying that how does this compare? So if you see this 0.8 means these Vietnamese names are correctly classified 80% of the times. Or some just like French. French is almost green, which is around French is correctly classified 60% of the times. So this is a confusion matrix, and it just says what is the quality of your network that you have learned. So it says so for each class what is the probability or what is the precision of that. So how much time or are you predicting correctly, how much you are correcting wrong and so on. And yeah, and you can just give some user input and say what it. So if you give say some input say Satoshi, so it is a Japanese one, but because our network is not well trained this time, so it is say with some score of say minus 0.58, it is Italian or Polish or Arabic. But if it was good, it would have said that with one probability one, it is Japanese. But since it is not trained well, we just give the confidence it has of various uh, various classification classes it may belong to. So this is a basic flow of any neural network task that you will be doing. Of course, for you need the code for hyperparameter tuning, for tuning the different uh, parameters such as number of iterations or learning rate. So, but the basic flow remains like this. You pre-process your data, create your vectors, then create your architecture, and write your training function, and you run it for a few, run it for some iterations, and then evaluate it on the test data. So I hope this flow is clear from this example. Are there any questions? So I have shared the link for this tutorial website. You can download it and play around with it on Colab or a local system if you have. Okay, so this is it for today. If you have any questions, we can discuss. Uh, Else, yeah, we can meet next week. I will share this notebook in the shared folder. You can also download it from there. Yes, I'll upload this video as well.